right. This will be our last content lecture of the semester. And we're going to talk about sound and musical stuff today. I wish we could do this for a whole week because it's really fun stuff. So you see I've got a pretty aggressive list. We'll talk some about this in lab tomorrow as well. But let's get right into it. So sound waves are a longitudinal wave. Do you remember from last class period what a longitudinal wave is?
It's a wave.
Horizontal.
Goes with the direction.
Okay, the displacement of the particles is the same direction as the wave is traveling. So, it wasn't on Friday. So a sound wave. Sound is coming out of my mouth right now. And what is happening is air molecules are moving. So it comes out of my mouth, they're moving like this. And then there's chain reactions. And so you have air molecules moving like this that get to you. So they're traveling this way and air molecules are moving that way, back and forth. Maxwell.
All right, this might sound weird, but I got a question. I've always wondered this. So watch this. Your ear, inside your ear, there's like a thing, right, that pushes a bone and it makes a vibration so your brain can understand, right?
Mm-hmm.
The sound.
Mm-hmm.
So like in music, you can hear like different frequencies, but it all has to be processed by one bone and one frequency. So like, how does that bone? So like in a band,
It doesn't. I mean,
you know what I'm
I
saying?
think
Right?
I have a picture of the ear later on, but your ear is very complicated. So your ear has the first line defense is that tympanic membrane, which is why they say you shouldn't use Q-tips to clean your ears because you can puncture it. I had my girlfriend clean my ear with Q-tips and punctured it. Yeah. So that tympanic membrane has two purposes really. Purpose number one is to keep the rest of the ear isolated from the outside world. But number two is it vibrates when sound waves hit it. And our ear has a ear canal. First you have the outer ear that's kind of big. For some of us, bigger than others. And so that's collecting sound waves and reflecting them in, and then those sound waves get condensed down so that we have actually more energy per unit area hitting that tympanic membrane than if it was just sitting out here. But then that tympanic membrane moves in and out, and then you have the bone you're talking about. You have the anvil and stirrup.
Yeah.
You have basically a bone that is a lever. And so this gets pushed in a little, and this here moves more because it's a lever, one side longer than the other. And so that amplifies the sound some more. And then that, it's not beating a drum, but it causes you to have then pressure waves that go down the cochlea. And the cochlea, you have these little cilia, these little hairs, if you will. And those hairs will vibrate with the sound waves. And that's what picks up the sound. It's those hairs vibrating. So we have lots of different hairs. Hairs of different length will pick up different frequencies, and that's how we pick up different frequencies. It's a pretty complex system, right? It's not just some simple thing. Okay, that was off topic for right now, but it's on topic for today. Three things necessary for sound. You have to have a source. Example of a source, I clap my hand. How does that make sound? How does that make sound? Percussively. No, it did. You heard it. It made air come out quickly from between my hands. Right before my hands touched each other, the space between them gets really small really quickly. It forces a lot of air out. And that's what makes the sound that we hear. So you have to have a source. Then you have to have a medium. That is, sound waves cannot travel in a vacuum. Remember, a vacuum means zero pressure or nothing present. Sound waves cannot travel through a vacuum. They have to have a medium. And then finally, listener. And notice I put a question mark with the listener. You guys have heard of those crazy philosophical questions, like how many angels can dance on the head of a needle? Or can God make an object too heavy for him to lift? Those are dumb philosophical questions. And then there's another one that says, If a tree falls in a forest and there's no one there to hear it, does it make a sound? What was that?
Yeah, same thing.
That is why I have a question mark there. Because that philosophical question, it's actually a question about existence. How do you know something exists if you didn't observe it? Right? So it's not the trivial question it sounds like. But in physics, we take a very pragmatic approach. We know that if a tree falls, it's going to make air move unless you're in a vacuum. And so it's going to make a sound. So we say, yes, it makes sound whether there's a listener or not. But there are some schools of thought that say, if you didn't observe it, you don't know if it happened. And so that's the point of that. Just to add one more thing to this, Bart Simpson answered to me, what is the sound of one hand clapping? Bart's all, that's easy. Okay, got that out.
Oh my goodness.
Description of sound. When we talk about sound waves, we talk about their pitch. I talked about a concert A in class on Friday. A concert A is a pitch, right? You go up from an A, you go to A sharp or whatever, right? You have different notes, B, C, D, E, F, G, no H. Pitch is measured in sound by the frequency. So we've just talked about oscillations. We know what frequency is. For sound waves, frequency is telling you what the pitch is. The higher the frequency, the higher the pitch. Lower the frequency, the lower the pitch. Then we have timbre, the quality of the sound. And I know it looks like timbre or something like that, but it's timbre. And the timbre, the quality of the sound, depends on the mix of frequencies. So we'll do a little demonstration today in class where we'll look at sounds and see the frequencies that make a sound different. So you can have two people sing the same pitch, but one sounds beautiful, one sounds raspy. And that's the timbre. That's the quality of the sound of the voice. And the difference is because they have different sets of frequencies present. It's not just one frequency when you sing. Now, as you'll see when you whistle, it pretty much is one frequency. Finally, we have what we colloquially call the volume. You know, the volume. If I tell you, what's the volume, you would answer, how would you answer?
How loud it is.
How loud it is. So, how loud something is depends on the amplitude of the wave. Now remember, what is amplitude? Okay.
The distance from the peak to the...
They were going for the technical. The maximum displacement you receive, which is from the equilibrium position to the displacement. Now for a longitudinal wave, this can be a little confusing. Because the air molecules are moving like this and the sound wave's moving like that, we usually take a sound wave and we'll make a transverse graph. We'll put displacement on the vertical axis and time or position on the horizontal axis, even though the displacement is in the same direction as the velocity. So you need to not get confused about that. We also, with a sound wave, we can talk about the pressure, because sound waves are pressure waves. I talked about the molecules coming out of my mouth. You can talk also about the pressure, because there's bursts of pressure coming out of my mouth. It's like I'm going, puh, 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 except for I'm doing it really quickly. How am I doing that really quickly? How am I making bursts of air come out of my mouth very quickly? Well, my diaphragm is pushing the air, but it's not causing bursts. My diaphragm, in and of itself, would just go, right? That's not much sound. Yeah, it's my vocal cords. My vocal cords, I have these little meaty things that go like this. And they slap closed and open again. And so I have bursts of air that come through. And then I have musculature that allows me to control those vocal cords, make them tighter or looser, so that I have different frequencies with which they will slap open and close. And that's how we adjust the pitch when we sing. Okay, go ahead. Okay, I have to talk about a few things before we get further into sound wave. And the first thing here is superposition. Sometimes I think of this as superimposition, because you superimpose them. You may or may not know, I didn't know until I got to graduate school, my teacher said, if you superpose the two waves, I'm going to superimpose, you superimpose them, don't you? They mean the same thing. So superposition is putting two waves on top of each other. If I have two waves and they meet, they just pass through each other and their displacements just add up. And so in this picture, I have wave one. This is not my own drawing, and you can see the asymmetry there. It makes me feel a little better about my own artwork. Although, what's the true problem here? The center line is not centered, it's too high. So we have this one here. If this is position on this axis, then this one here has a wavelength that's that long, right? Wavelength is the distance for it to repeat. And then this one here has a wavelength that's that long. They're very different wavelengths. And if I have these two waves, whether it's on a string, if I'm sitting here with a string going like this, or if it's two sound waves passing through each other, what's going to happen is I'm simply going to have the displacements add up. And so if you look at this resultant is going like, okay, that's my best of drawing what's supposed to be the green one, but then the green one, they're both green. The top one with then the small one oscillating about it. So you can see that they're just added up. So that's called superposition. When two waves pass through each other or meet, they simply add up. Go ahead.
So they don't have to be going opposite directions.
No.
They can be going like somewhat similar directions.
They can be exactly the same direction. They can be exactly the same direction. Because you have something like this. It's not making just one frequency, it's making multiple frequencies. And those frequencies are all traveling out together. And so if you look at the waveform that makes, it looks complicated because you have multiple frequencies involved. And we will. This here is showing if they are in phase. Now, what does in phase mean? If you have two waves that have the same frequency, and if they have their peaks at the same time, right? The bottom one is the addition. Then we call that in phase.
If you do this with string instruments, you can like feel it.
I suppose that's true. I don't play a string instrument.
I guarantee it's true.
Okay, so if I have two waves that are in phase, they will have constructive interference because when one's positive, the other's positive. You add the two positives together, you get a bigger positive. One's negative, the other's negative. You add the two negatives together, you get a bigger negative. So in this case, the resultant of these two waves superposing is that you have a resultant with twice the amplitude. So that's constructive because it got bigger. What if they were exactly out of phase? If when one was at its peak positive and one was at its peak negative? Then we have destructive interference, they add up to zero. So I have two waves traveling, and they add up to give me nothing. Destructive interference. There's more than meets the eye here because you have to think about energy. What happened to the energy? Well, energy that's not here has to be somewhere else. You can't lose it. You can't make or destroy energy. Standing waves is a situation that you get when you have waves going opposite directions. There's your opposite directions. For opposite direction motion, superposition, if you have the same frequency, will make it so some places you get constructive interference, some places you get destructive interference. The places where you have constructive interference, maximum constructive interference, we call those antinodes. The places where you get destructive, we call them nodes. Now notice at the antinode position, you can go from a big positive displacement to a big negative displacement. And sometimes it goes through zero. But at the node position, it's always zero displacement. So now we can talk about the energy and make more sense of it. The energy in the wave is proportional to the displacement squared. And so if you double the displacement there at the antinode, you have 4 times the energy. And of course, at the node, you have 0 displacement, you have no energy. And so you can see the energy is shifted because of the standing wave. Why is the standing wave important? That's the key to musical instruments. This is setting up a standing wave. Or setting up a standing wave. So standing waves are going to be what we're going to study in lab tomorrow and what we're going to talk about now. So a wave on a string. This beautiful musical instrument. Now I say beautiful musical instrument, it's really in bad shape. It's stripped so these screws don't hold it in place. Can't do a lot. But I have 2 different strings on here and I can tighten them independently and I can play sound. First thing we're going to do is if I pluck the string, I'm going to pluck it about the center. I pull it up and I let go. In terms of waves, what's going to happen when I let go?
It's going to go both ways.
I'm going to have waves traveling out in both directions because of me pulling it up here. Now, if I'm directly at the center, those waves are both going to get to the ends at the same time and come back, right? If I'm more over here, this one's going to reflect back first, this one reflects back second. It sounds different if I pluck different places. It's the same pitch, but it sounds different because of the different places where they meet. So I'm going to pluck this and I make a wave. Travels here and reflects back. First thing I have to talk about, which I don't have in the slides, probably going to come up in 3 slides and I'll say like, oh, there it is. If I have a wave, if I pull it up, it's an upward displacement, right? This is a transverse wave as opposed to a longitudinal wave like sound. That upward displacement comes here. This holds it in place. So this is pulling down. So what is the string going to do when it reflects back off of a place that was holding it in place?
Go the other way and kind of intermix and mess it up.
Well, it's going to reverse. If it was a positive pulse coming this way, when it reflects back from a fixed boundary, it's going to be a negative pulse. So it inverts the direction of the displacement. Now, if I had, instead of that, here it is. If I have this string here like this and I swing, okay, stop. If I swing it back and forth, there is nothing restricting the bottom of the string, right? And so when a displacement to the left gets to the bottom, it makes the swing left and then its momentum makes it swing out left even more. My left, your right. And so what happens when you get the wave getting to the end of an open or a non-constrained system like this is that it actually comes back with the displacement on the same side. So you have opposite effects. If it's constrained, so it's fixed in place, the reflection will have the opposite displacement. If it's free to move, it will be a reflection with the same displacement. So it's a different kind of reflection depending on what kind of end you have. Now, let's do something that's fun before I actually do this. I just want to do some fun stuff intermingled. So what I have here is our Pasco system. Can start recording. And what this is doing is it's recording the sound waves, the intensity of sound coming into this. I'm just going to shove this in the end here, and I'm going to pluck a string. I got to hit record. Okay, so there you can kind of see the waveform. Now, this is a low frequency, and I have my time so you can't see any repeating. That's no good. Now we can see it repeating. So if you look at this waveform, this is a complicated waveform. Why is it complicated? What makes it complicated?
Not only one wave or another.
It's not only one frequency. if you look, you can see that there is a periodicity, right? You go from this peak here, you have a whole bunch of stuff, then this peak here, a whole bunch of stuff. There is a little variation between those. In an idealized situation, it would look exactly the same from one to the next. And so what you have is multiple frequencies. Now over here we have what's called a Fourier transform. It's a fast Fourier transform that shows us the actual frequencies present. Unfortunately, mathematics being what they are, for us to have a nice clean looking waveform on the left, we have a really not very clear fast Fourier transform. So you can't see the frequencies all that clearly on the frequency one. If I spread it out, you just see these get to be pretty wide. But we have different frequencies present. And one thing that you will note is that the spacing between these peaks is about the same. And in fact, they are the same. It's just that the width of them makes it so it looks like some are wider and some are narrow, the gaps. So we have what we call overtones. We have multiples of the fundamental frequency. The fundamental frequency, okay. It's hard for me to hum it because it's so bad sounding. That's the fundamental frequency. All the other frequencies that you hear are integer multiples of that. So this here is somewhere around, let's say 170-ish, and then this would be 170. That's 170. Well, the next one would be like 340. So the fundamental must be down here somewhere, and this is the second harmonic, third harmonic, fourth harmonic, fifth harmonic, sixth harmonic. So we call those, hopefully I said that right. The fundamental is the first harmonic. Then the next one is the second harmonic, third, fourth, fifth, and so on. They're integer multiples of the fundamental. You might have heard the term overtone. Overtones are the same as harmonics except for you shift by one. The second harmonic is the first overtone. Third harmonic is the second overtone. So you get multiples of that fundamental frequency. Now, that's not a very good looking system, right? This here, because it's not making very good sound. So let's try something that makes better sound, like whistling. Oh, nice job. That looks really crummy because if you look down here, see this sampling frequency rate is 2.13 kilohertz. That's because I changed this over here. You can see the frequency that I was doing pretty clearly. I was doing about 870 hertz. But I want to change the sampling frequency so it looks smooth. Perfect. Come on. You see it moving. I hit stop. Okay, there we go. Now you can see there's the waveform for me whistling. Now if you look at that waveform, you see it's nice and sinusoidal. Whistling is pretty much a pure tone, one frequency. Now what's different from whistling? Singing. Yes.
Oh, yeah.
Y'all ready for this? I'm going to go ah. Ah. Really? Ah. There we go. Caught one. So here's me saying ah. Singing ah, whatever. You can see, yes, it repeats. And clearly it has more than one frequency there. I am going to now focus in on the frequencies. Zoom this in, which is going to change my sampling so my sampling looks cruddy. Notice I was singing at a pretty low frequency. I was singing somewhere around 400 hertz. So let's do this again. Okay, There you see the frequencies present. Was I really singing around 400 hertz? No, not even close. Here's the fundamental frequency. Once again, somewhere around 150 hertz. That's the note the pitch that I was singing, 150 hertz. And then you can see 2 times that, I have another peak. 3 times that, I have another peak. And it takes all of those peaks to make the complicated waveform that was me going ah. And so this here is the signature of the ah sound, or the vocal format. Yes?
Can you define the fundamental frequency again?
The fundamental frequency is the one we identify as the pitch, and it's the lowest one here, the one that everything else is a multiple of.
And it's the lowest one, but it produces the longest wavelength, right?
That's right. So that was ah. What if I sing E? Will it look the same? Max says or maybe Randy, I don't know. One of them says Absolutely. Come on up.
What if I don't want to?
Let's do it.
You don't require, right?
I don't know.
Just kidding. I'm kidding.
Okay, so go ah and then just change to E while you're singing, okay? That's got a clue. Notice it's very different set of frequencies for E than ah. Now he kept changing pitch. What was that about choir again?
Oh, yeah.
He kept increasing the pitch as he was going. But you saw there's a very distinct difference between the ah and the E. Different frequencies give it a different sound. And so when we talk, we are constantly adjusting the frequencies that are resonating. How do we do that? Is what? Not the vocal cords. The vocal cords are what's producing the basic, not embouchure, because we're not going.
Like the shape of the inside of our mouth.
The shape of the inside of our mouth. We're changing the resonance conditions in our mouth. Sound waves bounce around in our mouth. They bounce around our sinuses too, which is what gives different people different qualities. Like some people will have a really good vocal quality. It has a lot to do with their sinuses, actually. And so we change the shape of our mouth to adjust the resonance of different overtones and to get the different sounds. Now, my sister, for her undergraduate degree, she did speech pathology. And this is one of the things they work with, because they're working on trying to teach people to get over speech impediments. And one thing that she had a classmate that totally didn't believe is that there is no such thing as the I sound. That's right. It's I-E. I is 2 sounds put together. It's a vowel diphthong. I is the ah sound and the E sound smashed together. So you go, anytime you say I, you're starting with ah and ending with E.
Oh, you're right. No.
Everyone's like,
No. Wow. You did not.
And so when you say I, you are shifting your mouth as the sound comes out for the I sound. Now, we in America, we speak a relatively simple language as far as what we have to do with our mouths. But different languages, you have different things you do. So, and a lot of this stuff is just really, I think, important. How many people speak a second language?
Just
Okay, we have a few.
Like the rest of the world except for
If you learn to speak a foreign language as a youngster, you usually get a really good ear for it, right? And what research says is if you are exposed to the sounds of foreign language when you're young, then you will be able to differentiate those sounds when you're older. So like if you were exposed to people who use the sounds they use in French as a child, even if you didn't learn French as a child, you'll probably be able to hear and speak French better when you're an adult if you learn it, because your ear learned those sounds. So having grown up in Sierra Leone and Liberia, I think that I have a little bit of advantage just because there's a lot of different sounds in those languages that I learned in addition to the sounds in English, even though my entire, I don't know which language in Liberia this is, but my entire language knowledge from Africa is I learned one song. What, Randy?
He's an African.
Oh.
Yeah, exactly.
Just to be clear, Max, Africa is a very large continent.
For real?
Ancestrally, you're what, Nigerian? So,
No, Ghanaian.
Ghanaian. So that's why you and Michael were missed, because you're both Ghanaian.
Yeah,
Except for he's more closely tied.
sure he's probably doing that longer.
Well, his family's, he's one generation removed.
One generation. I am.
Oh, you are too? Ah. Okay, well then you're both closely tied. All right, that was not important to the lecture. Let's get back to looking at the slides and talking about resonance. So for a wave on a string, now I'm going to look at simple conditions. If I have a wave on a string and I pluck this, I have fixed ends on the string. So the ends of the string cannot move. If we're going to set up a standing wave, notice that's an if. If we're going to set up a standing wave, the points that can't move are what we call nodes. So we have to have a node at each end of our string. Now, if you look at this wave, how much of a wave do I have between those two nodes? Half. For one, it needs to be going the same direction and at the same amplitude. So here I have the length is equal to 1/2 wavelength for the standing wave. And so given that frequency is equal to the speed divided by the wavelength, that's one of the equations we learned on Friday. Then since my length is 1/2 wavelength, then wavelength is equal to 2L. I substitute that in. And so that's what we call the fundamental frequency that will resonate on my string. It only depends on the speed of the wave on the string and the length of the string. So how could I raise that fundamental frequency with this instrument? Okay, I can move the note. I can make it shorter. I'm just going to use this to shorten effectively the string. Now it's going to have a note here. So since it's a shorter length, what's going to happen to the frequency? It's a higher pitch. That's why if you play the cello, that's what you play, right? Or is it violin? Violin.
Same thing.
Okay. Well, it's in terms of the playing, yes. In terms of the instrument, no. So that's why you have your fingerboard and you touch lower down to shorten the string to make a higher pitch. Now, of course, there's another thing that you do before you do any concert, and that's tune your instrument. Important. What are you adjusting when you tune your instrument? I'm going to look at Anna, because I know she's gifted here. Well, I don't know if she's gifted at tuning. She's gifted at playing.
What about
How do you tune your instrument?
the tuning peg?
What do you do with them?
I turn them.
She turns them. She turns them and something magical happens. I'm sure you know what that magic is, though. What does it do to the string?
It tightens it.
It tightens it. So if I tighten it, what should it do to the pitch?
Higher.
It goes higher. If I loosen it,
Get lower.
it goes lower. Now the length between the nodes is staying the same. So L is staying the same. So what must be changing?
Length of the string between two.
No, I just said that's fixed.
That's the same.
What else is in that equation? 2 is not changing, just for the record. The velocity. The velocity must be changing as I tighten it. And as I make it tighter, the velocity goes up. If I make it looser, the velocity goes down. But then we have another thing. Some of your strings play high notes and some play low notes. What's the difference in the physical string between those?
The larger or like the size of the string. The lower it is.
Okay, the larger the diameter of the string, the lower its pitch. Well, this here has two strings, one that's a larger diameter, one's the smaller. And so if they're roughly the same tension, which I just assume they are, I don't have anything to measure it. The fatter one played the lower pitch. And that's the way it works with the violin, or viola, or cello, or, string bass. Because, say what? String bass? Because the speed for a wave on a string is the square root of the tension divided by the mass per length. And so the strings that are fatter have more mass per unit length, which makes the wave speed slower for those strings. And if you tighten them, you'll make the wave speed faster. So that's why we have those two things that come into play. Now, could Anna take the string that's designed for low pitches and use that for all the strings on her violin? Maybe. If you tighten it enough, you'll get to the right speed, right?
It will only go so far.
Yeah, it'll only go so far. What would happen if you actually tried to do that? You'd have really tight strings on one side and really loose strings on the other, and then the neck of your instrument would bend if you didn't break something else. So that's why they have strings with different densities rather than all the same string and use different tensions. You want to have them about the same tension. Now, you do use the same string for more than one, right? They're not a different string for each of the...
It's a different string.
It's different for each four?
Yeah,
Okay.
it's E, A, D, G. And it's going to be a different one for each instrument.
Yeah, well, they're different ones, too.
No, I mean, like, it'll be, like, a different string for each instrument. Like, there's no two strings that will be the same.
Now you mentioned density. Are you talking like the same material that it's made of?
Well, the density here is what we call the areal density, the mass per length, or linear density, mass per length.
Okay.
So it's the mass per length. So what you could do is you could start with the same string, and then you could wrap a really thin string around it, and that's going to increase the mass per length. Now, this here is what we call the fundamental frequency. But it turns out that you don't have to have a half wavelength between the two ends of the string. What you have to have is a node at each end of the string. So I could, notice there was another node out here. So I could make this so I had a standing wave like this. Now that's supposed to be at the center. My artistry is not perfect. How many wavelengths do I have in here? One. Each one of these loops is a half wavelength. Remember, it has to go, there's one, oh, that was the wrong button. I'm doing the positive and the negative. So at any point, the string is moving somewhere between these extremes. And so I can just take like the green and say that's what the string is at some instant. And the string is going half a wavelength to here, another half wavelength to there. And so in that case, my length is equal to a wavelength. So the frequency is equal to V over L. But then there's other options I could go with. I could fit 1.5 wavelengths in here. I could have it go like that. Then I would have the length is equal to 3/2 wavelengths. Frequency is equal to 3V over 2L. And now there's a pattern to be seen. Let me put a 2 over 2 here to make the pattern clear. I can have frequency is V over 2L, frequency is 2V over 2L, frequency is 3V over 3L, or in general, the frequencies that will resonate on the string, frequency sub n is equal to NV over 2L. So frequency 0, the fundamental frequency is that V over 2L. That's the lowest frequency that will resonate on my string. And then any integer multiple of that will also resonate. So this comes back to words we've already said. Harmonics. N equals 1 is the first harmonic, N equals 2 is the second harmonic, N equals 3 is the third, and so on. And so now you can see, hey, that's where they come from. That's actually really simple. This is a question I periodically have asked on tests. Let us say that you have a string and you find that the string has two adjacent harmonics with frequency N equals 330 hertz and frequency of N plus 1, the next available harmonic, is 390 hertz. Okay, I gave you an impossible situation. I was thinking about a different instrument. I could have that occur with an organ pipe. I can't have it occur with a string. So 330 and 360. If those are adjacent frequencies, what's the fundamental frequency? It's what?
330.
Not 330. Notice we have each of our harmonics is an integer multiple of our fundamental. So I have N times the fundamental is 330. N plus 1 times the fundamental is 360. Well, of course, N plus 1 times the fundamental is N times the fundamental plus the fundamental. Which means the difference in those two is the fundamental.
270.
No, the difference.
Oh, 60.
Getting closer, 30.
Wow.
So the fundamental here is 30, and then I can say, oh, if the fundamental is 30, then this is the 11th harmonic, because this is 11 times 30. This is the 12th harmonic. So just knowing that there are adjacent frequencies, I was able to determine what the fundamental frequency was. And if I know the fundamental frequency, and I tell you, for instance, what the speed of sound is, or speed of the wave is, then you could determine the length of the string. Or if I give you the length, you could determine the speed on the string. So here's the examples of the next two harmonics. Notice it calls them overtones. The first overtone is the second harmonic. And likewise, the second overtone is the third harmonic. So we've already gone through that derivation. Some math. Math that the gentleman tomorrow will appreciate. Is that right, Randy? If we describe a wave on a string, Y here is going to be the displacement. A, what would A stand for? Amplitude. Then we have sine of, what's omega?
Speed. Angular speed.
Angular frequency now. It was angular speed or angular velocity prior to this. Now it's angular frequency. Still the same units and whatnot, but we're describing something different. Multiply by time plus K.
Spring constant.
It sure seems like it should be, doesn't it?
Why do they switch so much?
But it's not. K is called the wave number. I know. K is constant. It's used all over the place. Now, given this relationship, I can tell you what the speed is and I can tell you what the direction is. And you probably are saying, how so, wise guy? Here's the rule. If we want to stay at one displacement, like let's say we're at where displacement is the amplitude, then we want this argument to stay constant. And so in this case, as time goes positive, what's x going to have to do for omega t plus kx to stay constant? It's going to have to go down. And so what that means is, as time increases, X is moving in the negative direction. So that's moving to the left. This one here has a minus sign. So in this case, as time goes up, what's X going to have to do to keep this thing constant? Increase. So this one here is going to the right. So if the signs of these are opposite, it's going to the right. If the signs are the same, it's going to the left. And then the second thing is if I'm staying on the peak, I need to have omega t plus kx equals a constant. Now I said staying on the peak. Let's make life easier. Let's make it stay on where it's 0 displacement. If we set that equals 0, that's real easy. Solve this for x. How do I solve that equation for x? Omega t plus kx equals 0. X equals
X equals negative omega t over k.
Well, we know that x is equal to vt, so that thing in parentheses must be v. So the velocity is negative, that's because it's going to the left, and it's omega over k. So we were able to calculate the velocity really quite simply from this. Now, why do we have these? If I have two waves on a string, and they're described by that, then here is the total, using superposition, displacement. And that's going to give us, if you add sinusoids, there are trig identities, as shown right here, that allows you to rewrite this. This is the same thing, to a cosine omega t sine kx. We have time variation and spatial variation. And so if kx is equal to an integer multiple of pi, then it's 0 and we get a node. So these are the places where kx is equal to an integer multiple of pi. And then in between, we have it moving up and down. So the nodes are defined by this here, the places where we have no displacement. So if I have two waves traveling through space and they go through each other, then I can have this kind of superposition. Some places I will have a loud sound because sine kx will be 1. Some places I'll have no sound because sine kx will be 0. I'm not sure why I have this slide this way. This is actually just review, and I don't have time to go through the review right now. I need to, we've already done this. I wanted to get to this, beats. And this will be my last trick. Here I have two little tuning forks mounted on resonating chambers. The resonating chambers are going to just make it so you can hear it louder. Now these two things look just alike. I am going to hit these one at a time. Got it? This one?
Same thing.
Now I hit them both at the same time. What's happening?
Kind of sounds like they're oscillating back and forth.
It's getting louder and softer. We call that beats. It occurs because those are not exactly the same frequency. Your ear couldn't tell, maybe Isabel's could, that they were different. But when they're played together, you have very slightly different frequencies. And so with superposition, here it's showing them, here they have perfectly in phase constructive interference and it's loud. Sometime later, they're out of phase, no sound. Then it comes back to loud again. And so the frequency of getting loud and soft is simply equal to the absolute value of the difference in the frequencies. So that had a beat frequency, as we call it, of 1 hertz, which means that this one here was 1 hertz lower frequency than this one was. This is how you can do something like tune a piano. You have these strings, And let's say you want two strings to have the same frequency. You play them both, and then you adjust the tension until there's no longer any beats. And then you know they're the same frequency. If you want them to be different by 3 hertz, you adjust the frequency until that beat frequency is 3 hertz, and you know it's different by 3 hertz. And of course, the one that's tighter is going to be the higher frequency. You have to pay attention to that. This is useful for things like flying an airplane. Let's say you have a twin prop. You want to take off. You throttle up and go. But here's something that wouldn't be very fun. Let's suppose that your prop on the right side is doing 5,000 RPM, and the one on the, I'm just making up no, I don't know what to do. The one on the left side is doing 4,000 RPM. They're both going to pull good, but the one on the right is going to pull more. And so when you let off the brakes, what are you going to do? That's no good. So what does a pilot do? You throttle up one, you throttle up the other, and you adjust the throttle until the beats go away. Then you know that they're rotating at the same rate. You let off the brakes and you're going to go straight instead of here.
That's how they do it.
That's at least the old school way. I don't know, back when I was in college, we had to fly twin props in and out of grad school, out of Washington State University there. And that's what they would be doing. So you hear them throttle one up, and then throttle up the other, and you hear the big frequency, and you hear it getting lower and lower frequency until they're the same, and it goes. All right, have a great day. I'll see you for Lab Manana. Last pre-lab quiz, last lab, last of everything.